Okay, this is part 4 of the review for the final exam, starting with number 27. Everything we're covering in this part of the video has to do with material that was covered after the last test. So number 27 is find the inverse function of f of x equals, I'm going to rewrite this one, x minus 3 to the 5th plus 8, and then state the domain and range of both the function and the inverse. So we think of this as y equals x minus 3 to the 5th plus 8. And then to find the inverse, you physically swap x and y. You switch the domain and range. So this will be x equals y minus 3 to the 5th plus 8. Then we're playing a kind of a game of re-isolate y. So we need to subtract over the 8. Get rid of the 5th power by taking a 5th root of each side. Now remember, if we were taking an even root, we would have to write a plus or minus, but we're not. So this is 5th root of x minus 8 equals y minus 3. And the final step on that would be to add the 3 over. And I'm going to go ahead and call this f inverse of x. Now you could write f inverse of x equals all of that, or this way, it doesn't matter. And then we want to talk about the domain and range of both the original and the inverse function. The original was a polynomial just in a transformative format, so that means that the domain is just negative infinity to infinity. That means that the range of the inverse is also negative infinity to infinity. The inverse came out as a root problem, but it was an odd root. Odd roots also have a domain of negative infinity to infinity, which means that the range of the original function shares that. So remember, the domain and ranges have just been swapped. And they're not very interesting in this case because it was a polynomial and an odd root radical. Things get a lot more interesting when you have rational functions or even roots, because then you have to worry about your restrictions. Okay, for number 28, we're trying to solve this for x, but x is an exponent. The only way we could solve this, well, there's two ways. If we can get the basis to match, then we can solve it by setting the powers equal. If we can't do that, then we would have to use logarithms. So I believe we can get both of these to be base 4. 64 is 4 to the 3rd, and then we would still have the 3x plus 2 on the outside. 16 is 4 squared, and we would still have our x minus 1 on the outside. Since we have two powers on the same base, we would multiply. So this would be 9x plus 6, and this one will be 2x minus 2. So our base on each side match, so now we can set 9x plus 6 equal to 2x minus 2. Subtract 2x over and get 7x. Subtract the 6 over, get negative 8, and divide by 7. So negative 8/7. Number 29 is a graphing problem. It's an exponential graph. We want to plot at least 3 points and dash in the asymptote. So the best way to deal with these usually is a table. If your exponent has something other than just an x, if it's a plus or minus something, you want to adjust the middle of your table. So x plus 3 needs to set equal to 0 to be centered. So this will be a negative 3. Then pick two numbers smaller and two numbers larger to plug in. So this will be e to the negative 5 plus 3 plus 1. So that's e to the negative 2 plus 1. So we use our calculator and our e button. Mine, I have to enter in the exponent first, so negative 2, and I want to be e to the negative 2, then plus 1. So 1.1, we're just going to round to one decimal place. E to the negative 4 plus 3 plus 1 would be e to the negative 1 plus 1. So a negative 1 exponent raised to the e power, or e to that power, and then that would be 1.4. E to the negative 3 plus 3, and then plus 1 is e to the 0 plus 1. E to the 0 is 1, so 1 plus 1 is 2. E to the negative 2 plus 3 plus 1 is e to the first plus 1. So just e plus 1. That will be 3.7. And then e to the negative 1 plus 3 plus 1 is e squared plus 1. Which is 8.4. We plot our points, so left 1, 2, 3, 4, 5, and then up 1.1. Negative 4 is at 1.4. Negative 3 is at 2. Negative 2 is at 3.7. And negative 1 is at 8.4. So a very slow grow, but we finally start seeing that upward direction. And then the asymptote is, if you're an exponential function, not a log function, but an exponential, your asymptote is horizontal and it happens at the vertical shift. So it happens right here. We don't ever cross below positive 1. Okay, so that's number 29. Number 30, to solve this equation, we have 5 and 24 and 4, which is kind of distracting. But we have all these bases that are not the same. So I don't think I'm going to be able to get the same base and drop them and then set the powers equal. I could try to isolate that 5 to the 2x, and I'm going to do that by dividing the 4 over, and that gives me 5 to the 2x equals 6. Again, 5 and 6 never will have the same base. We could convert this into a log since it's an exponential. So log base of argument equals exponent. So the base that we're talking about is the one that's attached to this x part. So this would be log base 5. The exponent goes on the other side, and then we have our 6 in the middle. So notice that this is not solved for x, but we could easily remedy that by dividing by 2. So that would be what we call the exact solution. Now, there is a piece to this. To get it rounded, we need to be able to do it on our calculator. So there's a change of base formula, which we're going to talk about more in class on Tuesday, that says if you want to calculate something like this, first of all, I'm going to pull the 1/2 out to the front, and then times, because that's this 2 right here. This would become the log of, if you want to do a change of base to base 10, which is what our calculator can do, you do the log of the argument, so log of 6, divided by the log of the base, which would be log of 5. So if we want to get the decimal approximation, which the directions do say we need to, this would be log of 6, which I have to enter my 6 in first, divided by log of 5, and then I want to times that by 1/2. So 0.56 if we're going to 2 decimal places. So this is what we call our rounded down here. It is important to know the difference. Okay, number 31 has us sketch the graph and dash in any asymptotes. This is going to be a log graph. When you're trying to graph a log function, the easiest way, especially if you're really good at tables, is to convert it to exponential form and just realize that you're going to have to pick y values to plot instead of x values. To do that, you want to write this as y equals log base 2 of x plus 3. You'll want the log to be isolated before you try to do any conversion, so nothing in front of it as a times or at the end as a plus or minus. If it's a plus or minus in the parentheses, it's part of the log. So once you've assured that nothing's there, if there is, you need to move it over first. Then you would turn this into exponential form by doing 2 to the exponent on the other side equals this. So 2 to the y equals x plus 3. Now, because I'm going to be doing my table by picking the y values this time, I always get x by itself. So I'm going to say subtract 3 over. So that gives me something really easy to plug into my calculator. So since there's nothing up here with the y that suggests that we need to offset our table, I usually just stick with -2 to 2. So we'll be doing 2 to the -2 minus 3, 2 to the -1 minus 3, 2 to the 0 minus 3, 2 to the first minus 3, and 2 to the second minus 3. I'm just going to work from the end backwards. 2 squared is 4 minus 3 is 1. 2 to the first is 2 minus 3 is -1. 2 to the 0 is 1 minus 3 would be -2. 2 to the -1 is 1/2 minus 3 would be -2.5. 2 to the -2 is 1 over 4 minus 3 would be -2 3/4. So we have our points. So -2 3/4 down 2, -2.5 down 1, -2 0, -1 +1, and 1, 2. So notice this is what a logarithm function looks like. They do have a boundary that they don't cross, and it's a vertical asymptote. And it's, notice wherever we were getting closer to, it has to do with what the domain is. The domain is that this has to stay greater than 0. So notice everything in our graph is greater than -3. That's our vertical asymptote. Okay, let's look at number 32. This one just specifically asks about the domain, range, and the asymptote for the log function. To find the domain, you have to make sure that the log's argument stays greater than 0. That has to do with, remember, this being an inverse of an exponential. So we set it greater than 0, and we get x is greater than -5. So for domain, -5 to infinity. The range of a log is all real numbers because exponentials had a domain of all real numbers. So because they're inverses, that makes the range everything. And then the asymptote, a lot of people try to use the -1 for something. It doesn't have anything to do with either of these. The asymptote has to do with the domain. So x equals -5 is the vertical asymptote. All right, let's look at 33. Looks like it would hopefully be one where you would try to get the bases the same and then try to set the powers equal. But in this case, you can't make 3 and 5 have the same base. So a trick that we learn is, and this is going to be covered in Tuesday's class, is that you can solve this by taking the log of both sides. As long as you use the same base on your log and do it to everything on both sides, it's legal. And then we're going to learn another property on Tuesday's class that says if you have a power in a log argument, it can be brought to the front. So this is now 2x log of 3 equals, bring the same thing here, x plus 1 log of 5. Notice I kept the x plus 1 in the parentheses because this log of 5 gets distributed to it. So this would be x log 5 plus 1 log 5, so just log 5. And then you want to try to get everything that has x on the same side together. So we're going to move those logs around. So 2x log 3 minus x log 5 equals log 5. We can pull the x out now as a GCF. And then we can notice that this is divisible by, if we want to solve for x, we would move this over by dividing that big parentheses over. Now, this is actually an acceptable exact form for some books. Other books want you to combine this back, so they want you to put the 2 back up as a power. So I'm going to show you some alternate forms of the same answer. So if we put the power back up, so any number in front can be put back up as a power, that would be 3 squared, so that would be 9. So this becomes 3 to the second. And we learn another property in 5.5 and 5.6 that says if you have subtraction between two logs that have the same base, you can combine it to one log and it becomes division of the first one divided by the second one. So the log is just one log and the argument parts are division. So this would be log of 5 over log of 9 over 5. So this is one way to write it. This is one way to write it. The original was one way to write it. And if you even want to get even more technical, there's the change of base formula backwards. You can pull this back down to being the base is the bottom one. So this would be log 9/5 as the base, and the argument is the top argument. So that would be the smallest we could make this so that it's a single log with just a base and an argument. But honestly, depending on your instructor, depending on how the textbook teaches it, some people say that all of these are acceptable versions of the same answer. Okay, for number 34, this is also from 5.5 and 5.6. There's a property that says if two logs are on the same side and they have the same base and they're separated by plus, you can combine them by making it multiplication of the arguments. So then this would be FOILed out. So that's 5x squared minus 5x minus 2x plus 2. Combine like terms. Now, if you have a natural log or a log of the same base on each side, and there's only one on each side, you can set their arguments equal. If we try to solve that, the 5x squareds would cancel out. Subtract over the 2. Divide, and we get 34 over 7. The problem with logs is that their arguments have to stay greater than 0. So what we just have to check really quick is that all of this, when it's plugged in, 34 over 7, will make each of these arguments greater than 0. So I just check them with my calculator if it's a fraction, just makes my life easier. So 34 divided by 7, and then times 5, and then minus 2. It's bigger than 0, so that one's a check. 34 over 7 is bigger than 1. If we subtract 1, that's going to still be greater than 0. 34 divided by 7, and then squared, because we're doing this one, times it by 5, and then minus 32. That is also greater than 0. So since all three of them have arguments that stay greater than 0 with this solution, it is correct. Okay, for number 35, we're looking at a similar case, except there's not logs on everything. So notice when there was logs on everything, we were able to drop the logs down and set the insides equal. If there's one thing that doesn't have a log, you can't solve it that way. You have to solve it using the spiral technique. We can still combine this because of the plus and these logs having the same base by multiplication of the two arguments. So this would be log base 3 of x squared minus 2x plus 4x minus 8. So that would be x squared plus 2x minus 8. Now, you cannot set this equal to 3 because there's not a log over here. So we have to convert this to an exponential. So 3 to the third equals x squared plus 2x minus 8. 3 to the third is 27. Subtract it over to be with the x's, and that would make that negative 35. That factors into x plus 7 and x minus 5. So I think I have two possible solutions of negative 7 and 5, but we've got to check our arguments. So I'm going to do a check for negative 7, and then I'll do one for 5. Just grabbing those arguments to check to make sure they stay greater than 0. The first one fails right here. Negative 7 plus 4 is not greater than 0, so this one's out completely. 5 plus 4 is definitely greater than 0. 5 minus 2 is also greater than 0, so positive 5 is the only solution. And then our final question on the review is number 36. It says use the compound interest formula to determine how long it will take $1,000 to double if it is invested at a rate of 6.5% compounded continuously. Okay, so compounding continuously means we're using the PERT formula. We did learn about that last week. Doubling our money, so that means our future value is $2,000. Our present value is $1,000. Our rate as a decimal would be 0.065. And remember, we don't know the time. That's what we're solving for. So 2,000 equals 1,000 e to the 0.065 t. I would divide the 1,000 over, so I just get 2 equals all of this. And then this is kind of a problem. What we're trying to solve for is a variable in the exponent spot. So if we take a log of both sides, and I'm going to use natural log because natural log is base e. So natural log of 2 equals natural log of all of this. Because of the power rule, we can bring this part to the front. That's the power rule of logarithms. That would still be natural log of e. Now, if you know that the base, see, a lot of people don't realize that natural log has a hidden base of e there. Natural log of e is 1 because you're saying e to what power equals its e, so it's equal to itself. But I'll show you that on my calculator. So let me find the e button. So e to the first, and then take the natural log of that, and you get 1. So for these, that natural log of e will always end up being just a 1. So to solve this, we just need to divide by 0.6065. And that'll be our time. So natural log of 2 divided by 0.065 is 10.66 years. And that's it for the final review for the final exam.